Hello friends, in the previous lecture we learned the concept of refrigeration. How do we get refrigeration effect into a space by using a refrigeration system? We learned that how second law of thermodynamics restricts us to supply continuously the ample amount of work so as to get refrigeration effect through a refrigerating system. We also learned the concept of coefficient of performance. We learned different types of refrigeration system. In that lecture, we also learned the cooling capacity in terms of tons. 1 ton of cooling capacity of a refrigeration system is the capacity that freezes 1 ton of liquid water at 0 centigrade into ice at 0 degree centigrade in 24 hours. So this heat removal rate comes out to be around 3.5 kilowatt. So 1 ton of cooling capacity of a refrigeration system is equal to 3.5 kilowatt. In today's lecture, we will develop the understanding of different types of refrigeration system, including vapor compression refrigeration cycle, gas refrigeration cycle, absorption refrigeration cycle, and different areas of applications where refrigeration systems are being used. Vapor compression refrigeration cycle. In the previous lecture, we learned that it includes 4 main components, including compressor, condenser, expansion valve, and an evaporator. The processes carried out in these components are represented on TS diagram. We can see that 1 to 2 is an isentropic process represented as a vertical line. Since the area under a line on TS diagram gives us the heat exchange value for that process, since the area under 1 to 2 line is 0, that means no heat is exchanged during this process. So basically compression process is reversible adiabatic process, or we can call it isentropic process. 2 to 3 is a process carried out inside a condenser where at constant pressure heat is rejected, and we can see that how temperature is decreasing from T2 to T3, and also its phase is changing. The refrigerant at point 2 is in superheated vapor region, but because of heat rejection ultimately it is transformed into liquid phase. So at point 3 it comes out as saturated liquid. Afterwards we have an expansion valve, and usually in refrigeration system we use a capillary tube to get expansion of high pressure refrigerant, and we see this throttling process for this expansion of the refrigerant from 3 to 4, and finally at 4 point the refrigerant at low pressure and low temperature is achieved. At 4 point it enters into an evaporator. Since at point 4 the temperature is so low that the space around the evaporator gives its heat to the refrigerant that is flowing inside the evaporator coils, and hence from 4 to 1 heat is absorbed from the space where we require cooling effect, and because of heat absorption from 4 to 1, liquid refrigerant will transform into vapor, and at state 1 we get saturated vapor. As I said, the area under a line on TS diagram represents heat exchange value. So the area under line 4 to 1 gives us the heat absorbed from the refrigerating space. So this is the refrigeration effect, and the area under 2 to 3 gives us the heat rejected by the condenser. If we are interested in calculating COP for the system in vapor compression cycle, the refrigerant will either be in vapor phase or in liquid phase. But we have another refrigeration system called gas refrigeration system, where the refrigerant will always remain in gaseous state. This kind of refrigeration system is based on reversed Brayton cycle, and the same cycle is termed as gas refrigeration cycle. The cycle is represented as in this diagram. You could see that it includes 4 main components. 1 to 2, the process is carried out inside a compressor, and for a compressor we always require some kind of work that can compress the working fluid. From 2 to 3, we have heat exchanger, where heat is being rejected by this heat exchanger, since during the 1 to 2 process the compression work will increase the internal energy of the refrigerant, so its pressure and temperature both will rise, as we can see the same effect in TS diagram. The 1 to 2 process represented as a vertical line on TS diagram, that means compression process was carried out isentropically, and we can see that the temperature at 2 is quite higher than the temperature at 1, and the pressure is also very high. Since the refrigerant at state 2 is having high temperature, it is higher than its immediate environment, so in the heat exchanger the heat, because of temperature difference, is lost to the environment and the refrigerant get cooled, and we can see this cooling process of the refrigerant inside this heat exchanger from 2 to 3 process, represented on TS diagram as well, and we see QH amount of heat is rejected, and as a result the temperature will decline from T2 to T3. But during this process the pressure remains constant, so it is a constant pressure heat rejection process. At 3, the refrigerant will enter into a turbine, where it will expand from 3 to 4. During this expansion process the pressure will decrease and temperature will also decrease, and since the turbine is extracting some amount of work by this expansion process, so this work is given back to the compressor, and that's why turbine and compressor both are shown on the same shaft. At 4 point we see the temperature has become very low. It is so low that in the following component, that is another heat exchanger, where we require some refrigeration effect, we get refrigeration effect because of this low temperature at state 4, and in this way the refrigerated space will provide the required heat for the refrigerant to get heated from state 4 to state 1, and again the cycle is repeated. So basically this is a reversed Brayton cycle which include 4 processes. 2 are isentropic processes and remaining 2 processes are constant pressure processes. 1 to 2 and 3 to 4 processes are isentropic processes, and 2 to 3 and 4 to 1 processes are constant pressure processes. This kind of cycle or this kind of refrigeration systems are basically very suitable for aircraft cooling and cryogenic applications, because this kind of system have lighter components, so it makes them suitable for aircraft cooling. In contrast to vapor compression cycle and gas refrigeration cycle, in case of an absorption refrigeration cycle, we do not use any compressor. In vapor compression and gas compression cycles, we had used compressor for compression task, but instead of a compressor, in absorption refrigeration cycle, we use a complex setup as shown in the dotted box, where we have different components which are doing some task in order to get the same effect as we had got with the help of a compressor in previous 2 cycles. Basically, in absorption refrigeration cycle, we have 2 mediums. One, the refrigerant, the second, a carrier of the refrigerant. Most widely used refrigerant in such a cycle is ammonia, and water is used as a carrier or transport medium. Now, what we see in the box is that pure ammonia is entering to an absorber where the pure ammonia is absorbed by water. Since ammonia absorption depends on the temperature of the water, so we want to keep the temperature of water as low as possible, and for that reason we use a cooling water stream which is continuously cooling the absorber. Since this mixing process of ammonia and water is an exothermic reaction, so there will be some heat generation, and the cooling water will take away this generated heat from the absorber. Now, at the end of this absorber, we see a pump. The pump will take this mixture of ammonia and water and pressurize it up to very high pressure and supply it to a generator through a regenerator. In the generator, we use some source of heat which is supplied to this rich mixture supplied to the generator. Because of the heating of the mixture, ammonia vapor is generated, and rich ammonia and water vapor will be supplied to rectifier which separates ammonia vapor from water, and the water is supplied back to the generator, and this lean solution now collected inside the generator will be supplied back to the absorber through a regenerator and an expansion valve. Since the pressure in the generator is higher as compared to absorber, So to decrease the pressure of this lean mixture, we require an expansion valve. And since the lean mixture of water and ammonia, which is coming from generator to absorber, is having some heat, so this heat is exchanged in the regenerator and supplied to the rich mixture coming from the pump. Now, after the rectifier, the pure ammonia vapor is supplied to the condenser where it is liquefied after heat rejection and expanded as we had done in case of vapor compression cycle. After expansion valve, we get very low temperature and very low pressure ammonia liquid, which we supply to evaporator and get refrigeration effect. So in this manner, absorption refrigeration cycle works. Absorption refrigeration cycle are primarily used in large commercial and industrial installations. Since these are complex and less efficient systems, so basically we use them when we have cheaper thermal energy available to us. Otherwise, the most popular and most widely used vapor compression cycles are used. Applications of refrigeration systems. Refrigeration systems are used for household refrigerators, for industrial freezers and chilling plants. They are also used in cryogenic industries, for air conditioning purposes in industries as well as in households. It is also used for heat pump applications. For packaging and transportation of perishable items, refrigeration systems are also used.